And I'm from Microsoft. So this is the agenda for the presentation. We'll be introducing the work briefly, and we'll be covering the related work in similar areas. Then we'll talk about why it is a revolutionary idea that we present in the paper. We'll talk about the architecture of a system, the experimental results, and then finally conclude the paper. So in the recent past, we have seen surge of different types of advanced malware, especially in this work from home culture that we have got into. We see a lot of attacks from ransomware and very advanced metamorphic malware. So metamorphic malware are kind of malware that can change the structure or mutate, which makes the detection very difficult. So even if the malware enters and it infects a system, you are able to capture it or detect it. By the time you put defenses around it, it may have mutated to another form that might be undetectable. So in this paper, we present a system called ADVERSARIALuscator, which is a novel AI-based metamorphic malware generator and obfuscator. In fact, it cannot just generate some malware, but it can generate a swarm of malware which can overwhelm any advanced intrusion detection system or malware detector with that swarm, which will act like a zero-day attack on that system. Obviously, we do not create actual malware which can take to such a doomsday, but we create synthetic generations, and we create enough safety in our mechanism such that it could be used for negative purposes. And we cover those safety as well in the later. So as compared to other systems which create adversarial attacks on malware detectors, ADVERSARIALuscator is unique in the form that it has multiple capabilities. It may not only be used for similar work that other system use, but also more effective way in the same case. But it can also be used to train or develop auxiliary systems than the main detector to work. And it can also be used to normalize or negate the obfuscations of a particular malware such that it could be brought to the original strain. So now let's cover some related work. Most of the related work in this area is connected to GANs, which is generative adversarial networks, a typical type of convolutional neural network architecture, which is used to generate new images. And it is very popular. Code base is available in most of the popular deep learning libraries. And this is being used to create binary perturbations. So in this particular approach, malware is laid down in the form of like a CNN map or two-dimensional map, which is put against these GAN networks. And then these GAN networks learn how to evade those low-level binary intrusions. Most of this comes from gradient-based approaches, and we'll talk about why gradient-based approaches is not a very good idea. In the recent past, in the last 2-3 years, we have seen some reinforcement learning-based approaches also coming up for similar reasons that the earlier GAN-based approaches didn't scale to making an actual impact in the real-life systems. So reinforcement learning mechanisms have come up, but because of the state-of-the-art then, most of these reinforcement learning have limited themselves to Q-learning, and Q-learning has its own limitations, especially in the case of the cardinality of both state and action space. And in case of deep Q networks, it is mostly the action space. Because of which these networks as used could only work on very low cardinality space, and which translates into very low information features. And hence they could only work at the level where the file could not be identified as a file or couldn't actually create a malware, but they're just trying to evade those a particular malware detector which is based upon very low end features, and that the file couldn't be actually replicated to a malware, which translates into the fact that the malware, even after it has been evaded in experiments, in real life it is not expecting any of those features to be coming because those features are mostly coming from random perturbations that couldn't be assembled back to a particular file. Now, this is also the gaps that we find in literature. We do not find any AI-based obfuscation or metamorphism system which can create an actual malware, or at least a representation of actual malware, such that a system is likely to encounter one day. Now, why we believe that obfuscation and creating metamorphic malware at this level is revolutionary. So first of all, as we discussed, that existing art, whatever exists, can only create perturbations, mostly at a very low feature level, maybe at binary level, permissions level, or something that cannot be converted into a particular file, or if a particular new file is converted to that file, it may be highly unlikely that it will take the exact same form as in those feature spaces that has been used to evade this particular event. The second problem with the existing system is that most of these systems are based upon gradient attacks. And if we train something using gradient attack and retrain the classifier using a data that has been created by evading gradient attack based techniques, then it is more likely that we are deteriorating the classifier instead of improving it. There's several reasons to that, and many researches have been done around those things. And the third point is the moment you retrain a particular classifier with new data, and obviously if the classifier is not changing, if it has limited learning capacity, it will learn new things only at the cost of giving less weightage to the existing things that it has learned, which means now we are increasing the weights on something we are not likely to face anytime in the future, or very little likely, but we are forgetting or compromising the performance on the existing. So let's understand why obfuscation is actually a very complex problem. We understand the advantages of it as compared to any binary perturbations, but why obfuscation is a complex problem. The first factor is to create obfuscation, you need to change the file at either a code level, which is like a high level, and which is very unlikely a malware defender would do, because this could be misused rampantly. So the lowest level at which a functionality of the file could be preserved is at the opcode level. Lower than that, if you go and if you start changing or inserting any thing, then you are most probably corrupting the particular file, and that file couldn't be corrupted. Because there exist packets of a system only at the opcode level. That's the lowest level at which a file could be reassembled using advanced technology. The other important factor is that at this particular level or opcode level, you can target specific systems. So at this particular level, you can have like different instruction sets or opcode set for, say, Android, different for iOS, different for Windows, and different for Linux. We can create very robust defenses against all of them. Now we understand the architecture of the ADVERSARIALuscator. So what you see on the right is actually the process diagram that we use, which is like a detail level of an abstraction on the middle. So in the middle, what you see is a typical functioning of a reinforcement learning system, where on the top you see there is an environment and an agent, and the agent interacts with the environment to learn new things. And then it is put into production into something actually that it needs to govern. And the training environment and the validation environment or the actual environment can be different. The same thing happens in our case also. There are many challenges once we are trying to convert the problem of obfuscation into a Markov decision process. The first challenge is of the reward function. So if you just give a reward to the agent to make a file undetectable, it may actually behave in a very difficult manner, because then it may just reach a probability of 0.5 and stop over there, where it is not confirmed that at 0.5 level, all the detectors or classifiers would be able to reclassify that particular file. So we need to actually keep different types of reward functions. One, a linear reward function to see how much it can gain up to, and second is a step reward function to see if it's successful in the first level or not. And then we need to see if I can actually minimize the number of turns in which it can perform. So this makes the reward function slightly complex, and there are many techniques involved to normalize it to a given reward function. This is covered in the paper. And as mentioned earlier, we use a safe code obfuscation mechanism such that whatever we do as malware defenders, it cannot be used by malware developers. Practically, we make inherent systems which is covered in our paper, such that no one could make an actual malware to infect a particular system, but the system could be used to train other systems for defenses of newer types of malware. And secondly, we talked about functionality preserving. This is a very important criteria, because most of the systems that try to do a lot of different things around adversarial techniques or around what they claim is malware doesn't actually even preserve the functionality of the file. And without this, most of the things are not realistic, and the intelligent detection system is not likely to face any such file in the near future. And the second important point is, if the functionality or the main functionality of the file is not preserved, then it is actually not a metamorphic malware that we are trying to defend against. And we train multiple agents out of it, and each agent try to learn different strategies. All of these agents are based on different types of instantiations of an algorithm called proximal policy optimization, which is an improvement of an earlier algorithm under the policy reinforcement learning techniques called trust region policy optimizations. So these algorithms make possible to work on very large cardinality action space and even continuous action spaces. Next, we present the experimental results and observation that we see. So on the left-hand side, you see training graphs of a particular agent in terms of the instantaneous rewards and the total rewards that it has achieved across different epochs of learning. And we see like at the later end, it has started learning a lot of different new ideas to convert a particular malware into undetectable malware. And the dataset that we take of a mixed variety of metamorphic malware, and the ideas that we had used is coming from one of our earlier works, which has till date produced the best possible results on that particular dataset. And why it was able to produce the best possible results for, because it uses very sophisticated deep neural networks to do a lot of work internally. The end-to-end architecture, not just the classifier, but also a preprocessor and everything that is embedded inside the environment, ensures that most of the files, more than 90% of the files, actually reach a probability of non-malicious detection, which is, and that is why any uplift that we do from here is considered like a probability of non-detectable metamorphic file. So we found out that at least 1/3 of the samples were clearly raised to the probability that it is being considered as benign or non-malicious by the system. And on an average for the entire data set, the probability of considering as non-malware was raised up to 0.45. On the right, we draw similarity graphs with the feature vector of the metamorphic variant to its original variant, and we see like they are very similar. This actually proves multiple things. So first of all, it proves that for each file, it is learning a different way to obfuscate it, because this is the problem with reinforcement learning that is not addressed in many papers. So reinforcement learning agents, especially the more complex ones, and may actually learn a very trivial techniques to receive very high rewards, and it doesn't mean that they are learning the actual thing that you meant them to learn. So we believe that there should be some checks and balances to ensure that the agent is not learning very clever tricks that we are not able to decipher, and that is why we keep these checks. The second reason why it is very significant is because nowadays there is a layered sort of approach in detection. That layering approach and routing approach serve two purposes. Number one, it increases the performance on false positives and recalls. Number two, it ensures that similar viruses actually goes to, or similar malware goes to the same classifier, whose potential could be increased for those specific types of malware. Now, if the similarity is high, which means there is very high probability that it will reach to the same classifier where the original variant was going, and if it can actually evade an original variant, it can also easily evade the newer variant. So which means now if it is learning in labs to evade a particular classifier, then if it's routed to again a similar classifier, it will easily evade. So in conclusion, we would like to say that we designed a very novel AI-based system that we name ADVERSARIALuscator that uses deep reinforcement learning agents in the realm of policy approximation, to be more specific, PPO-based agents that could learn how to obfuscate a malware, and has a potency to generate data simulating a swarm attack or zero-day swarm attack from actual metamorphic malware. The system learns how to obfuscate a file at opcode level, which is the lowest level at which the functionality could be preserved, and hence it could be called an obfuscation and not just random part operations. The insights from the experiments prove that the system is capable of learning how to obfuscate a particular file. With this, I would like to say thank you.